Imagine right now, somewhere above your head, a droplet is falling from space. It's tiny, smaller than a grain of sand. So small you could never see it with your naked eye. But this droplet is different from anything else in the universe. It's made of something that shouldn't exist on Earth. The droplet enters our atmosphere moving at thousands of kilometers per second. It doesn't burn up like a meteor. It doesn't slow down. It just falls, slicing through the air like it's not even there. And then it touches down in the middle of the Pacific Ocean. The moment it makes contact with water, something happens, something irreversible. The water molecules around the droplet don't boil, they don't evaporate, they simply change. Atom by atom, molecule by molecule, the water transforms into something else, something grey, something lifeless. And here's where it becomes a nightmare. The change doesn't stop. It spreads, not like fire spreading across paper, not like a wave crashing on a beach. This is different. This is exponential. One water molecule becomes strange. Then that molecule touches another. Now there are two. Those two touch two more. Now there are 4, then 8, then 16, then 32. Within 1 second, trillions of atoms have converted. Within 1 minute, the conversion has spread kilometers in every direction. The ocean doesn't look any different yet, but beneath the surface, a grey sphere is growing, consuming everything it touches. 10 minutes later, the conversion reaches the ocean floor. It doesn't care that rock is different from water. It converts rock just as easily. Now it's spreading through the Earth's crust, moving in all directions at once, up toward the surface, down toward the mantle, outward in every direction. 1 hour later, the first signs appear on the surface. Somewhere in the Pacific, the water takes on a strange grey colour. Ships in the area would see it if anyone was looking. But by the time anyone notices, it's already too late. 6 hours later, the grey has spread across the entire Pacific Ocean. It touches the coast of California, the coast of Japan, the coast of Australia. Beaches turn grey. Cities near the water experience something no one can explain. Buildings don't collapse. They just change. The metal, the concrete, the glass, all of it transforms into the same grey substance. 12 hours later, half the planet has converted. Europe is gone. Africa is gone. Most of Asia is gone. The conversion is moving through the Earth's mantle now, approaching the core. The planet is being rewritten from the inside out. 24 hours after that single droplet touched the ocean, it's over. Earth is now a perfect grey sphere, slightly smaller than it was before because the matter has compressed into something denser. There are no oceans, no mountains, no valleys, just a smooth, featureless ball of grey matter. Everything is gone. Every person who ever lived, every memory ever made, every painting, every song, every story, every tree, every animal, every microbe, all of it converted into the same substance, not destroyed, not vaporized, just transformed. And the worst part? This grey sphere is stable, more stable than anything that existed before. It will sit there in space for billions of years, forever unchanged, forever silent, forever dead. The question you should be asking yourself right now is this: what could possibly do this? What substance could have this power? The answer has a name. Scientists call it strange matter. And by the end of this video, you're going to understand exactly why this nightmare could become real. Chapter 1. What everything is made of. Let's start with something familiar. You. Me. This device you're using to watch this video. The chair you're sitting on. The air you're breathing. All of it is made of the same basic building blocks. We call them atoms. Now, you probably learned about atoms in school. You might remember that they have a nucleus in the center and electrons orbiting around the outside, kind of like planets orbiting a sun. That's a good start, but we need to go deeper, because the nucleus itself is made of smaller things, protons and neutrons. Protons have a positive electric charge, neutrons have no charge at all, and together they make up almost all the mass of an atom. But here's where things get interesting. Protons and neutrons are not the smallest things. They're not fundamental particles. They're made of something even tinier, something so small that we can barely imagine it. These particles are called quarks. Think of quarks like the ultimate building blocks, like the smallest Lego pieces in existence. Everything we see, everything we touch, everything that has mass in the normal universe is built from these quarks snapping together in different combinations. Now, there are actually 6 types of quarks in total. Scientists have given them strange names: up, down, strange, charm, top and bottom. But for our story today, you only need to remember 2 of them: the up quark and the down quark. These 2 quarks are the ones that build normal matter. Here's how it works. Take a proton. Every proton in the universe is made of 3 quarks. Specifically, 2 up quarks and 1 down quark. That's it. That's the recipe. 2 ups, 1 down, and you get a proton. Now take a neutron. A neutron is also made of 3 quarks, but the recipe is slightly different. 1 up quark and 2 down quarks. 1 up, 2 downs, and you get a neutron. These quarks are held together by the strongest force in nature. We call it, quite simply, the strong nuclear force. It's the glue that holds quarks together inside protons and neutrons, and it's incredibly powerful. So powerful that under normal circumstances, quarks can never exist alone. They're always locked inside protons and neutrons, bound together by this tremendous force. This is important to understand. In the normal universe, the universe you and I live in, quarks are prisoners. They can't escape. They can't roam free. They're trapped inside their particles, and that's how they stay for billions of years. Your body right now contains trillions upon trillions of atoms. Each atom has a nucleus with protons and neutrons. Each proton and neutron contains 3 quarks, and every single one of those quarks has been locked inside its particle for longer than Earth has existed. This is stability. This is the normal state of matter. But what if we could change the rules? What if we could apply so much pressure, so much force, that even the strong nuclear force couldn't keep quarks locked up anymore? What would happen then? To answer that question, we need to leave Earth behind and journey to the most extreme places in the universe. Chapter 2. The Birth of a Monster. Let's talk about how stars die. Because death in space is where our story truly begins. Stars are massive balls of burning gas. Our Sun, for example, has been burning for about 4.5 billion years, and it will keep burning for another 5 billion years before it runs out of fuel. But when a star much bigger than our Sun runs out of fuel, something spectacular and terrifying happens. The star collapses, not slowly over millions of years, rapidly. In less than a second, the entire star falls inward on itself. The outer layers crash down toward the core with incredible speed. And when they hit the core, they bounce back, creating a massive explosion called a supernova. The explosion is so bright it can outshine an entire galaxy for a brief moment. But we're not interested in the explosion. We're interested in what's left behind. After the fireworks are over, after the outer layers have been blown into space, something remains at the center. A tiny, dense object called a neutron star. Now, when I say tiny, I mean tiny by cosmic standards. A neutron star might be only 20 kilometers across, about the size of a city. But here's the insane part. That little ball contains more mass than our entire Sun. Imagine taking something bigger than 1,000,000 Earths and crushing it down to the size of Manhattan. That's a neutron star. The density is almost impossible to comprehend. Let me give you a comparison that might help. If you could somehow take a single teaspoon of neutron star material and bring it to Earth, that teaspoon would weigh more than Mount Everest. More than every human being on Earth combined. More than all the buildings, all the cars, all the ships, and all the planes put together. This density creates pressure. Unimaginable pressure. The pressure inside a neutron star is billions upon billions of times greater than the pressure at the center of Earth. It's so intense that the normal rules of matter break down completely. In normal matter, atoms are mostly empty space. The nucleus is tiny and the electrons orbit far away, relatively speaking. But in a neutron star, there's no space left. The pressure is so great that it crushes atoms completely out of existence. The electrons get squeezed into the protons. When an electron and a proton merge, they form a neutron. So the entire star becomes essentially one giant atomic nucleus made almost entirely of neutrons, packed together as tightly as physically possible. That's why we call it a neutron star. It's not really a star anymore. It's a ball of neutrons. But here's where we need to go even deeper. Because neutron stars aren't all the same. Some of them are even more massive than others. And in the absolute most massive neutron stars, the ones at the extreme end of what's possible, the pressure at the very core becomes so intense that even neutrons can't hold themselves together anymore. Think about what that means. Neutrons are already incredibly compressed. They're already packed as tightly as the strong nuclear force allows. But at the heart of the most massive neutron stars, even that isn't enough. The pressure overcomes the strong force itself. When this happens, the neutrons start to dissolve. Not into atoms, not into protons and electrons. They dissolve into their components, into quarks. The up and down quarks that we talked about earlier, the ones that are normally locked inside neutrons, suddenly break free. At this point, the core of the neutron star is no longer made of neutrons. It's made of a sea of loose quarks. Quarks that aren't bound inside individual particles anymore. They're swimming freely in a soup of other quarks. Scientists call this quark matter. And it's here, in this environment of unthinkable pressure and density, that something very strange can happen. Chapter 3. Meet the strange quark. Remember when I told you there are 6 types of quarks? We talked about UP quarks and down quarks because those are the ones that make up normal matter. But now we need to introduce you to the 3rd member of this family, the strange quark. The strange quark is heavier than the up and down quarks. It has more mass. And under normal circumstances, strange quarks don't appear in regular matter at all. They're too unstable. When particle accelerators create strange quarks in experiments, they decay almost instantly, transforming back into lighter quarks in a tiny fraction of a second. So in the normal universe, strange quarks are basically irrelevant to everyday life. They pop into existence for a brief moment in cosmic ray collisions or particle physics experiments, and then they're gone. They don't build anything. They don't last. They don't matter. But inside the core of a neutron star, the rules are different. The pressure changes everything. Under that immense crushing force, strange quarks can appear. And more importantly, they can stay stable. They don't decay. They don't disappear. They join the soup of up and down quarks that used to be neutrons. When up quarks, down quarks, and strange quarks all mix together in the right proportions, they form something new, something that has never existed on Earth. We call it strange matter. Now, here's where we get to the truly unsettling part. There's a theory in physics, and I want to emphasize that it's just a theory, but it's a theory that some very smart people take seriously. The theory says that strange matter might be more stable than normal matter. Let me explain what that means using an analogy. Imagine you have a ball sitting on the side of a hill. The ball isn't rolling down because there's a little dip in the hillside where it's resting. It's stable there. It will stay there unless something pushes it. This is like normal matter. Normal matter is stable. It doesn't just fall apart on its own. Atoms last for billions of years. But now imagine that further down the hill there's a valley, a much deeper, much lower place where the ball could rest. If the ball could somehow get over the lip of its little dip and roll down to the valley, it would sit there even more stably. It would be in a lower energy state. And in physics, systems always want to move to the lowest energy state possible. This is the terrifying possibility with strange matter. Normal matter might be like that ball on the hillside. It's stable, yes, it works fine. It's been working fine for billions of years. But it might not be in the lowest possible energy state. Strange matter might be the valley, the true lowest energy state that matter can achieve. If this is true, then every atom in your body, every atom on Earth, every atom in the sun and the stars, is technically living in a higher energy state than it needs to be. We're all like balls sitting in that little dip on the hillside, not realizing there's a valley below us. And here's the nightmare scenario. If normal matter ever encounters strange matter, it might convert. It might roll down that hill into the valley. It might transition from its current stable state into the even more stable state of strange matter. Think about what this means. You are made of normal matter. Up quarks and down quarks, arranged in protons and neutrons, arranged in atoms, arranged in molecules, arranged in cells. That's you. But if strange matter is truly more stable, then your current form is not the ultimate form. There's a lower state you could be in. Right now, you're not in that state, because nothing has triggered the transition. It's like the ball needs a push to get out of its dip and start rolling downhill. But if something did trigger it, if your atoms encountered strange matter, they would see that lower energy state and they would want to transition to it. And once the transition started, once the first atom converted from normal matter to strange matter, there would be no way to stop it, because now that converted atom would be touching other normal atoms. And those atoms would see the strange matter and they would want to convert too. This is the heart of the nightmare. This is why strange matter is potentially the most dangerous substance in the universe. Not because it's explosive, not because it's radioactive, but because it might be contagious. If strange matter is truly more stable than normal matter, then the entire universe as we know it is living on borrowed time. Everything we see might be in the wrong state. And all it would take is one encounter, one touch, one moment of contact between normal matter and strange matter to start an irreversible cascade that would rewrite the universe itself. Chapter 4. The conversion process. Let's slow down and walk through exactly what would happen if a particle of strange matter touched a normal atom. Because understanding this process is key to understanding why this is so terrifying. Imagine a single atom. Let's say it's a carbon atom, the kind that's in your body right now. This carbon atom has a nucleus made of protons and neutrons. Those protons and neutrons are made of up quarks and down quarks, bound together by the strong nuclear force. The atom is stable. It's been stable for billions of years. It will stay stable for billions more unless something disturbs it. Now, a particle of strange matter approaches this carbon atom. The strange matter particle contains up quarks, down quarks, and strange quarks all mixed together in a stable arrangement. When the two particles get close enough, something called quantum tunneling can occur. In the quantum world, particles don't behave like solid objects bouncing off each other. They exist as probability waves. And one of the weird properties of these probability waves is that particles can sometimes pass through barriers that classical physics says they shouldn't be able to cross. This is quantum tunneling. It's not science fiction, it's real, and it happens all the time at the atomic scale. When the strange matter particle gets close to the carbon atom, the quarks inside the carbon atom's nucleus can sense the strange matter. And if strange matter truly is a lower energy state, those quarks experience something like a force pulling them toward that state, like a ball at the edge of a cliff feeling the pull of gravity. The quarks inside the carbon atom start to rearrange. The up quarks and down quarks begin to mix with strange quarks from the strange matter particle through quantum tunneling. The strong nuclear force, which normally keeps quarks locked in their specific patterns, gets overwhelmed by the pressure and density of the situation. And then, in a fraction of a nanosecond, the conversion happens. The carbon atom's quarks reorganize themselves into the strange matter pattern. Up, down, and now strange quarks mix together. The atom doesn't explode, it doesn't release a burst of radiation, it simply becomes strange matter. But here's where the nightmare truly begins. That carbon atom is not alone. It's surrounded by other atoms. Atoms that are still normal matter. And now this newly converted strange matter atom is touching those neighboring atoms. The process repeats. The neighboring atoms sense the strange matter. Their quarks tunnel toward the lower energy state. They convert. And now there are 2 atoms of strange matter where there used to be normal matter. Those 2 atoms touch 4 other atoms. Those 4 convert. Now there are 6 atoms of strange matter. Those 6 touch 12 more. Those 12 touch 24 more. This is exponential growth. 1 becomes 2, becomes 4, becomes 8, becomes 16, becomes 32, becomes 64. Let me put this in concrete numbers so you understand the speed we're talking about. Quantum processes happen fast, incredibly fast. Let's say conservatively that each atom takes 1 microsecond to convert and trigger the conversion of one neighboring atom. 1 microsecond is 1/1,000,000th of a second. After 1 microsecond, you have 2 atoms of strange matter. After 2 microseconds, 4 atoms. After 10 microseconds, about 1,000 atoms. After 20 microseconds, about 1,000,000 atoms. After 30 microseconds, about 1 billion atoms. After 40 microseconds, about 1 trillion atoms. And we're still not even at 1/10th of 1 second yet. By the time a full second has passed, if this conversion continues unimpeded, you've converted more atoms than exist in the entire solar system. The exponential growth is so rapid that it defies human comprehension. Now, in reality, the process might not be quite that fast. There might be factors that slow it down slightly. Different materials might resist conversion differently. But even if we slow it down by a factor of 1,000,000, we're still talking about a conversion that spreads through solid matter in minutes rather than seconds. And here's the crucial point. The conversion doesn't stop. It can't stop, because each newly converted atom is more stable than the atoms around it. Each converted atom creates a pressure, a quantum pressure that drives neighboring atoms to convert as well. It's like a fire that feeds itself. Each burning piece of wood ignites the next piece, which ignites the next, which ignites the next. Except this fire doesn't destroy matter, it transforms it. And it doesn't care what the matter is made of. Carbon, oxygen, nitrogen, iron, silicon, water, rock, metal, flesh, bone, all of it converts at the same basic speed. Because at the quark level, all normal matter is the same. It's all up quarks and down quarks, waiting to become strange matter. The conversion releases a tiny amount of energy as the matter transitions to the lower energy state. This energy helps power the conversion of neighboring atoms. It's a self-sustaining reaction. Once it starts, there is no way to stop it. You can't freeze it. You can't contain it. You can't run from it. The strange matter doesn't care about temperature, pressure, or any other physical condition. It just converts. This is why strange matter is potentially more dangerous than any other substance we can imagine. It's not a bomb that explodes and then stops. It's not a poison that kills living things but leaves dead things alone. It's a fundamental rewriting of matter itself. And once it starts, it continues until there is no normal matter left to convert. Chapter 5. Strangelets, the infectious particle. Now we need to talk about how strange matter might actually reach Earth. Because strange matter doesn't exist here naturally. If it exists at all, it exists in the cores of the most massive neutron stars, trillions of kilometers away from us in deep space. So how could it ever get here? The answer lies in something called a strangelet. A strangelet is a small clump of strange matter. Not a whole neutron star, just a tiny piece. Maybe a few hundred quarks bound together. Maybe a few thousand. Maybe a few million. But small, incredibly small. Potentially smaller than an atomic nucleus, or maybe as large as a grain of sand, but always incredibly dense. Here's how strangelets might form. Imagine two neutron stars orbiting each other. Over millions of years, they spiral closer and closer together as they emit gravitational waves. Eventually, they collide. The collision is one of the most violent events in the universe. The impact releases more energy in a single second than our Sun will emit in its entire lifetime. When neutron stars collide, pieces of them get thrown off into space. Most of this material is just normal neutron star stuff, superdense neutrons that will eventually decay back into normal matter. But if the cores of those neutron stars contain strange matter, chunks of that strange matter could be ejected as well. These chunks are strangelets. They fly off into space at tremendous speeds, thousands of kilometers per second, maybe even a significant fraction of the speed of light. And once they're out there in space, they just keep going. Because in the vacuum of space, there's nothing to slow them down. Another way strangelets might form involves the early universe. In the first microseconds after the Big Bang, the universe was incredibly hot and incredibly dense. Hot enough and dense enough that quarks existed freely, not bound inside protons and neutrons. As the universe cooled, those quarks started binding together to form normal matter. But some physicists think that in certain regions, strange quarks might have been abundant enough to form strange matter instead. If that happened, strangelets from the Big Bang could still be floating through space right now, billions of years later. A third possibility involves cosmic rays. Cosmic rays are high-energy particles that constantly bombard Earth from space. Most of them are just protons moving at nearly the speed of light. When these cosmic rays hit the upper atmosphere, they create cascades of secondary particles. Occasionally, they might hit other objects in space first, like neutron stars. If a cosmic ray with enough energy hit a neutron star, it might knock loose a piece of the star's core. If that core contains strange matter, you've just created a strangelet that's now flying through space. so strangelets might be out there. Right now, moving through the galaxy at enormous speeds. And here's the unsettling part. They would be invisible to us. Strangelets are too small to see with telescopes. They don't emit light. They don't emit radio waves. They're electrically neutral or only slightly charged, so they don't interact strongly with electromagnetic fields. They're essentially undetectable until they hit something. Think about the size we're talking about. A strangelet the size of an atomic nucleus would be about 10 femtometers across. That's 10 quadrillionths of a meter. Even a strangelet the size of a grain of sand, which would be huge by these standards, would only be about 0.5 millimeter across. You could fit millions of them in a teaspoon. But don't let the small size fool you. These things would be incredibly heavy. Remember, they're made of the same material as neutron stars. A strangelet the size of a grain of sand might weigh several tons. A strangelet the size of a marble could weigh as much as a mountain. All that mass compressed into a tiny volume. The density makes them almost indestructible. You couldn't break a strangelet with any tool we have. You couldn't vaporize it with a laser. You couldn't crush it in a press. The strong nuclear force holding the quarks together is simply too powerful. A strangelet could sit on the surface of a star and not melt. It could pass through a planet and not break apart. And because they're so stable, strangelets don't decay. A normal particle made of strange quarks would fall apart in a fraction of a second. But if strangelets are stable, they could exist for billions of years. A strangelet formed in a neutron star collision when the universe was young could still be out there, drifting through space, waiting to hit something. Now, here's the question that should be keeping you up at night. How common are strangelets? Are they incredibly rare, with maybe 1 or 2 in the entire galaxy? Or are they common, with millions of them flying through space right now? We don't know. We have no idea. We've never detected one. We don't know how many neutron star collisions create them. We don't know if they formed in the early universe. We don't know if cosmic rays create them. We're essentially flying blind on this question. If strangelets are incredibly rare, we might be safe. The galaxy is vast. The distances between stars are enormous. Even if strangelets exist, the chances of one hitting Earth might be so small that we could wait trillions of years without ever encountering one. But if strangelets are common, then we're just lucky. Lucky that one hasn't hit Earth yet. Lucky that we exist in a tiny window of time before conversion. Lucky that we're here to wonder about this at all. And that's the truly unsettling part. We have no way of knowing which scenario is true. We're sitting here on Earth, made of normal matter, with no way to detect strangelets until they arrive. No way to prepare, no way to defend ourselves. Just hoping that they're rare enough that we'll never have to find out what happens when one touches our planet. Chapter 6. The Earth Scenario. Let's walk through what would actually happen if a strangelet hit Earth. Because understanding the timeline and the mechanism is crucial to grasping just how powerless we would be to stop it. Our strangelet is moving through space at about 5,000 kilometers per second. That's not unusual for objects in space, it's about average for cosmic debris. As it approaches Earth, it's completely undetectable. No telescope can see it, no radar can track it. It's just too small and doesn't reflect enough light or radio waves. The first warning we would have is when it arrives. The strangelet enters Earth's atmosphere. At this speed, most objects would burn up from friction with air molecules. We see this all the time with meteors streaking across the sky as they vaporize in the upper atmosphere. But our strangelet is different. It's so dense that air resistance barely affects it. The air molecules in its path simply convert to strange matter as it passes through. The strangelet doesn't slow down. It doesn't heat up significantly. It just keeps going. The journey through the atmosphere takes less than 1/10 of a second. The strangelet passes through clouds, through the troposphere, through everything, and then it hits the surface. Let's say, for this scenario, it hits the Pacific Ocean somewhere between Hawaii and California. The moment of impact is silent. No explosion, no splash, no light show. The strangelet, which might be the size of a grain of sand, but weighs several tons, simply punches into the water and continues downward. But the instant it touches that first water molecule, the conversion begins. Water is H2O, 2 hydrogen atoms and 1 oxygen atom bound together. Those atoms contain protons and neutrons. Those protons and neutrons contain quarks, and the moment the strangelet touches them, those quarks start to convert. The first million water molecules convert in about a microsecond. They don't look any different from the outside. Water converted to strange matter would still be dense, still be cold, still be relatively clear. But at the quark level, everything has changed. Those molecules are now strange matter, and they're touching other water molecules. The conversion spreads in all directions, up, down, left, right, forward, backward. It's not moving through the water like a projectile. It's transforming the water wherever it touches. The boundary between strange matter and normal matter expands in a perfect sphere, growing larger every microsecond. After 1 second, the sphere of strange matter is roughly 10 meters across. That doesn't sound like much, but remember, this is exponential growth. It's not growing at a constant rate, it's accelerating. After 2 seconds, the sphere is roughly 100 meters across. After 3 seconds, roughly 1 kilometer. The growth is so fast that it would appear as if the strange matter is moving faster than the speed of light, though it's not. It's just that every point on the boundary is converting matter simultaneously. The strangelet itself doesn't matter anymore. It's long gone, either sunk to the bottom of the ocean or incorporated into the growing sphere of strange matter. The conversion is now self-sustaining. It doesn't need the original strangelet. Every atom that converts becomes part of the infection, driving the conversion of neighboring atoms. After 1 minute, the sphere of strange matter is roughly 100 kilometers across. It's no longer just water. The conversion has reached the ocean floor and is now moving through rock. Solid rock converts just as easily as water. The quarks don't care about molecular bonds or crystal structures. They just convert. Ships on the ocean above the conversion zone would notice something strange. The water would take on a grey color. But before anyone could investigate, before anyone could send out an emergency signal, the conversion would reach the ships themselves. The metal hull would convert. The crew would convert. Everything would become strange matter in an instant, so brief that there would be no time for pain, no time for fear, no time for anything. After 10 minutes, the conversion has spread across an area larger than Alaska. It's moving through the Earth's crust now, heading toward the mantle. Islands in the Pacific disappear. Not in fire or flood, but simply transforming. One moment they're there, the next moment they're grey and featureless. After 1 hour, the conversion reaches the coast of North America. Los Angeles, San Francisco, Seattle, entire cities convert in seconds. Buildings don't collapse, they just change. The concrete, the steel, the glass, the people, the cars, the trees, everything becomes the same grey substance. At the same time, the conversion is moving downward. It's reached the Earth's mantle, that layer of hot, slowly flowing rock that makes up most of Earth's volume. The heat doesn't slow the conversion. Temperature is irrelevant at the quark level. The mantle converts just as quickly as the crust. After 6 hours, half the planet has converted. Europe is gone. Africa is gone. Most of Asia is gone. But people on the unconverted side of the planet still don't know what's happening. Communications have been cut. Satellites have gone offline as they passed over the grey zone and converted. Power grids have failed. The internet is down. People are confused, scared, but they don't know the magnitude of what's occurring. The conversion continues to spread. It's approaching the Earth's core now. That incredibly hot, incredibly dense ball of iron and nickel at the planet's center. The core converts just like everything else. The pressure doesn't stop it. The heat doesn't stop it. Nothing stops it. After 12 hours, 3/4 of the planet is strange matter. The remaining unconverted regions are experiencing unprecedented earthquakes as the planet's internal structure changes. But these earthquakes don't last long. Within minutes, those regions are converted too. After 18 hours, it's over. Earth is now entirely strange matter. Every atom that used to be part of a planet is now part of a smooth grey sphere. The sphere is slightly smaller than Earth was because strange matter is denser. The surface is perfectly featureless. No oceans, no mountains, no valleys, no rivers, no clouds, just grey. The planet is still orbiting the sun. Gravity still works the same way. But everything else is different. The temperature has equalized. There's no atmosphere because there are no free molecules to make an atmosphere. There's no magnetic field because there's no moving molten core. There's no life, no movement, no change, just a ball of strange matter, perfectly stable, perfectly uniform, perfectly dead. And it will stay that way forever. Strange matter doesn't decay. It doesn't erode. It doesn't change. In 1 billion years, that grey sphere will look exactly the same as it does now. In 1 trillion years, the same. Long after the sun has burned out and become a white dwarf, long after the galaxy has changed beyond recognition, that grey sphere will still be there. A tombstone, a memorial to everything that once existed here. This is the nightmare scenario. This is what could happen if a strangelet hit Earth. No warning, no defense, no escape, just conversion. The end of everything we know, not in fire, but in transformation. And the worst part is, we would have absolutely no way to stop it. Once it started, we would be as powerless to prevent it as we would be to stop the sun from rising. Chapter 7. Has this already happened? If strangelets are so dangerous, if they can convert entire planets to strange matter in a matter of hours, then why hasn't Earth been converted already? Why are we here, made of normal matter, wondering about this possibility instead of being part of a grey sphere? This is actually a really good question, and it has several possible answers. The most obvious answer is what philosophers call the anthropic principle. We exist, therefore it hasn't happened. If a strangelet had hit Earth at any point in the past, we wouldn't be here to ask the question. The fact that we're here asking means that, by definition, it hasn't happened yet. But that doesn't tell us anything about the future. It doesn't tell us anything about the likelihood of it happening tomorrow or next year or in the next billion years. It just tells us that we've been lucky so far. So let's think about frequency. How often do strangelets hit planets? We don't know. We have no data. But we can make some educated guesses based on what we do know about other cosmic phenomena. If strangelets are formed primarily by neutron-star collisions, we can estimate how many might be floating around the galaxy. Astronomers observe neutron-star collisions occasionally. We detect the gravitational waves they emit and the light from the resulting explosion. In our galaxy, we estimate these collisions happen maybe once every 10,000 years or so. Each collision might eject anywhere from 0 to millions of strangelets, depending on whether the neutron star's cores contain strange matter and how the collision occurs. So the number of strangelets being produced in the galaxy is highly uncertain. It could be 0, it could be billions per year. Then we have to consider how those strangelets spread through the galaxy. They're moving at thousands of kilometers per second, which sounds fast, but space is vast. The distance between stars is measured in light years. Even moving at a significant fraction of the speed of light, it would take a strangelet decades or centuries to travel from one star system to another. So the density of strangelets in any given region of space is probably very low. Even if they're being produced regularly, the galaxy is so large that any particular planet might wait millions or billions of years between encounters with a strangelet. This is encouraging, but it's not proof of safety. It just means the odds of being hit on any given day are very small. But given enough time, even unlikely things eventually happen. There's another piece of evidence that makes some physicists feel better about the strangelet threat. It's called the cosmic ray argument. Cosmic rays, those high-energy particles constantly raining down on Earth from space, have been hitting our planet for billions of years. If strangelets were common in space, some of those cosmic rays would be strangelets. And if strangelets were hitting Earth regularly in cosmic rays, we would already be converted. But we're not converted. We're still here. So either strangelets don't exist, or they're rare enough that they're not showing up in cosmic rays, or there's something about small strangelets that makes them not dangerous in the way we've been discussing. This last possibility is important. Remember, for a strangelet to be dangerous, it has to be stable at small sizes. Some theoretical models suggest that while large chunks of strange matter might be stable, very small strangelets, like the ones that might be in cosmic rays, would actually be unstable. They would fall apart quickly before they could trigger conversion. If that's true, then we might be safe from naturally occurring strangelets in space. The ones small enough to be common might not be stable enough to be dangerous. And the ones large enough to be stable might be rare enough that we'll never encounter one. But again, this is all theoretical. We don't have experimental evidence. We can't make strangelets in a lab to test these ideas. We can't study the cause of neutron stars directly. We're working with mathematics and physics theories, trying to predict what happens in conditions we can never recreate. Some scientists argue that the very fact we exist is strong evidence that strangelets aren't a real threat. They point out that the universe has been around for almost 14 billion years. Countless planets have formed in that time. If strangelets were both common and dangerous, we would expect them to have converted most of the visible matter in the universe by now. The fact that we see normal matter everywhere we look, in every galaxy we can observe, suggests that either strangelets don't exist, or they're not infectious in the way we've been describing, or they're so rare that conversion events are incredibly uncommon. This is comforting, but it's not absolute proof. The universe is vast beyond human comprehension. Even if strangelet conversion were happening regularly on a cosmic timescale, we might not be able to see it. If a planet in a distant galaxy got converted to strange matter yesterday, we wouldn't know. The light from that event wouldn't reach us for millions of years. And even when it did, how would we recognize it? A grey sphere billions of light years away doesn't look very different from any other dead planet. So the honest answer to the question, has this already happened, is we don't know. It hasn't happened to Earth, obviously, but it might have happened elsewhere. It might be happening right now, somewhere in the universe, and we would have no way to know. And that brings us to the uncomfortable conclusion. We're making judgments about our safety based on absence of evidence. We haven't seen strangelets, so maybe they don't exist. We haven't been converted, so maybe it's not dangerous. But absence of evidence is not the same as evidence of absence. The universe is not obligated to give us warning signs. It's not required to provide proof before something catastrophic happens. We could be completely wrong about strangelets being rare. We could encounter one tomorrow, and we would have no way to prepare, no way to detect it, and no way to stop it. This is the uncomfortable reality of cosmic threats. We can calculate probabilities and make theoretical arguments, but ultimately we're at the mercy of the universe. And the universe, as we've learned again and again throughout history, is far stranger and more dangerous than we ever imagine. Chapter 8. Could we create strangelets? There's another source of strangelets that we need to talk about, and this one hits much closer to home. What if we accidentally created a strangelet ourselves? What if, in our pursuit of scientific knowledge, we triggered the exact catastrophe we're trying to understand? This question is not hypothetical. It was seriously debated in the years leading up to the activation of the world's most powerful particle accelerator, the Large Hadron Collider, or LHC, at CERN in Switzerland. The LHC is an enormous machine, a circular tunnel 27 kilometers around, buried underground near Geneva. Inside that tunnel, scientists accelerate protons to 99.9999% of the speed of light and then smash them together head-on. The collisions are incredibly energetic, recreating conditions that existed in the first moments after the Big Bang. The goal of these experiments is to understand fundamental physics. By colliding particles at high energies, scientists can create new particles and study the forces that hold matter together. The LHC famously discovered the Higgs boson in 2012. Confirming a crucial piece of the standard model of particle physics. But before the LHC was turned on, some people raised a concern. If you're recreating conditions similar to the early universe, conditions of extreme energy and density, couldn't you accidentally create something dangerous? Specifically, couldn't you create a strangelet? Think about what happens in these collisions. Protons are made of quarks. When you smash protons together at enormous energies, those quarks can break apart and recombine in different ways. The energy of the collision can create new types of quarks, including strange quarks. And if you have up-down and strange quarks all mixed together in a small volume, you might form strange matter. If even a microscopic strangelet formed in the LHC and turned out to be stable, it would sink to the bottom of the detector. Then it would continue sinking through the floor, through the rock beneath the detector, through the Earth itself. And as it passed through normal matter, it would potentially convert that matter to strange matter. The conversion would start small, but as we've discussed, it would be exponential. In a matter of hours or days, the entire planet could be converted. The human race would have accidentally ended itself in the pursuit of scientific knowledge. This is a genuinely terrifying scenario, and CERN took it seriously. Before turning on the LHC, they commissioned multiple safety studies. Teams of physicists examined the risk from every angle. They asked, is it possible to create dangerous strangelets in particle collisions? The answer they came to was almost certainly not. And here's why. First, the energy requirement. While the LHC is the most powerful particle accelerator ever built, it's not even close to the energies found in neutron star cores. The collisions in the LHC create temperatures and densities that are similar to conditions in the early universe, but they're nothing compared to the sustained crushing pressure inside a neutron star. The conditions simply might not be extreme enough to create stable strange matter. Second, even if the LHC could create strange matter, the amount would be tiny. We're talking about maybe a few dozen quarks bound together at most. And here's the crucial point. Small strangelets might not be stable. Theoretical calculations suggest that strange matter needs to be fairly large to be stable. Below a certain size, the quarks on the surface of the strangelet become unstable and the whole thing falls apart in a fraction of a second. Think of it like a water droplet. A large water droplet is stable. It holds together due to surface tension. But if you try to make a water droplet with only 10 water molecules, it doesn't work. The surface effects dominate and the molecules fly apart. The same might be true for strange matter. A large chunk might be stable, but a tiny one might not be. Third, and most convincingly, there's the cosmic ray argument we mentioned earlier. Cosmic rays hit Earth's atmosphere all the time with much more energy than the LHC produces. Some cosmic rays have energies thousands or even millions of times higher than anything we can create in a lab. If high-energy collisions could create dangerous stable strangelets, cosmic rays would have already done so countless times over the past 4.5 billion years. But Earth is still here. We haven't been converted. So either those cosmic ray collisions don't create strangelets, or the strangelets they create aren't stable, or they're not dangerous in the way we've been discussing. Based on all these arguments, CERN concluded that the risk of creating dangerous strangelets in the LHC was negligible, not zero, because in science you can never say the risk is absolutely zero, but so close to zero that it wasn't a reasonable concern. The LHC has now been running for over a decade. It has performed millions of particle collisions. And Earth is still here. We haven't created any dangerous strangelets. This is reassuring evidence that our understanding of the physics is correct. But it raises a broader philosophical question. Should we even be doing these experiments? Should we be probing the fundamental nature of reality if there's even the tiniest chance of catastrophic consequences? Some people say no. They argue that the risk, however small, is not worth the potential knowledge gained. After all, if we're wrong, if our calculations are off, if there's something we don't understand, the consequences would be total. Not just for humans, but for all life on Earth, for the planet itself. Other people, including most physicists, argue yes. They point out that we take risks all the time in the pursuit of knowledge. Every time we split an atom, every time we launch a rocket, every time we develop a new technology, there are risks. But the benefits of understanding the universe outweigh those risks. And in this particular case, the risk is so small, based on both theoretical calculations and empirical evidence from cosmic rays, that it's not reasonable to stop the research. My own view is that the cosmic ray argument is quite compelling. If something bad were going to happen from high-energy particle collisions, it would have already happened naturally. The fact that Earth has been bombarded by cosmic rays for billions of years without converting to strange matter is strong evidence that the process either doesn't happen or doesn't lead to runaway conversion. But I also think it's important that we're having this discussion, that scientists and the public are thinking about these risks, calculating the probabilities and making informed decisions. Because particle accelerators will only get more powerful. The LHC is not the end of the line. Physicists are already planning next-generation colliders that will reach even higher energies. And while each step up in energy probably doesn't change the risk significantly, it's worth continuously reassessing. Making sure we understand what we're doing. Making sure we're not inadvertently triggering something we don't fully comprehend. The Strangelay's question also connects to a broader theme in science and technology. As our capabilities increase, as we gain the ability to manipulate matter and energy at more fundamental levels, we're playing with increasingly powerful forces. And with that power comes responsibility. The responsibility to think carefully, to calculate risks, to proceed thoughtfully rather than recklessly. So far, we've been fortunate. Or perhaps more accurately, our understanding of physics has been good enough to keep us safe. But the question remains, how long can we continue pushing the boundaries before we encounter something truly dangerous? Something that our theories didn't predict? Something that our calculations got wrong? These are questions without easy answers. But they're questions we need to keep asking as we continue exploring the fundamental nature of our universe. Chapter 9: A Universe of Strange Matter. Let's expand our view now and think about what strange matter might mean not just for Earth, but for the entire universe. Because if strangelets exist and they're infectious, the implications go far beyond our little planet. Imagine that somewhere in the galaxy right now, a strangelet hits a planet. Maybe it's a planet orbiting a star 100 light-years away from us. Maybe it's in another galaxy entirely. We're not there to see it, but let's imagine what happens. The planet converts, just like we described for Earth. Within hours or days, the entire world becomes a grey sphere of strange matter. But the story doesn't end there, because that planet is orbiting a star. And eventually, either through orbital decay or just random chance, some of that strange matter might fall into the star. When strange matter enters a star, what happens? The star is made of hydrogen and helium, normal matter undergoing nuclear fusion. But the moment strange matter touches those atoms, they start to convert. The conversion spreads through the star's outer layers. Within days or weeks, the entire star has become strange matter. A star made of strange matter wouldn't burn the way normal stars do. There would be no more fusion, no more light. The star would collapse slightly, becoming denser and more compact, and then it would just sit there. A grey ball of strange matter where a bright yellow star used to be. From our perspective on Earth, if we were watching this happen, we would see the star suddenly dim and disappear. We might think it had gone supernova or turned into a black hole. We would never know that it had actually been converted to strange matter. But it gets worse, because stars don't exist in isolation. They're part of star systems. Our Sun has 8 planets, countless asteroids, comets, and other debris orbiting it. Other stars have similar systems. When that star converts to strange matter, eventually some of that matter will find its way to the other planets in the system. Asteroids might collide with the strange matter star and get converted, then drift toward other planets. The planets themselves might migrate inward and touch the converted star. One by one, everything in that star system would become strange matter. And then, on much longer time scales, the infection could spread between star systems. Space is mostly empty, but it's not completely empty. There are clouds of gas and dust between stars. Objects occasionally get ejected from star systems and drift through interstellar space. If any of that material touches the strange matter from the converted star system, it converts too. Then that material drifts to another star system and converts that one. The process would be slow on human timescales. It might take millions of years for the infection to spread from one star to a neighboring star, billions of years to cross a galaxy. But given enough time, if this process is happening, it would be inevitable. A wave of conversion spreading through the cosmos, turning every star, every planet, every bit of matter into the same grey substance. Some scientists have proposed that this might be a solution to the Fermi paradox. The Fermi paradox asks, if intelligent life is common in the universe, where is everybody? Why haven't we detected any signals from alien civilizations? Why does the universe seem so empty? One possible answer: they're gone, converted to strange matter. Maybe intelligence commonly arises in the universe. Maybe civilizations build advanced technologies and start exploring their galaxy. But then they encounter a strange lay. Or they create one accidentally in a particle accelerator experiment. Or one just happens to hit their home planet. And in a matter of hours, that entire civilization is erased. Not destroyed by war or disease or environmental collapse, but simply transformed into lifeless grey matter. If this has happened many times throughout the galaxy, it would explain why we don't hear anyone. We're alone not because intelligence is rare, but because intelligence is fragile. Because no matter how advanced a civilization becomes, no matter what technologies they develop, they remain vulnerable to this one fundamental threat. A threat they cannot detect, cannot prevent, and cannot survive. This is a dark interpretation of the universe. It suggests that life is not just rare, but temporary. That any accumulation of complex matter, any organization into living systems, is living on borrowed time. That the default state of the universe is not stars and planets and life, but strange matter, and that we're all just waiting for the conversion to reach us. Now, before you sink into complete existential despair, I should point out that this is highly speculative. We have no evidence that strangelets are common. We have no evidence that conversion is happening anywhere in the universe. This is a theoretical worst-case scenario, not a proven fact. But it's a reminder of our place in the cosmos. We think of Earth as solid, permanent, real. We think of the atoms in our bodies as stable, unchanging, fundamental. But physics tells us that nothing is truly permanent. Everything is just a temporary configuration of energy held together by forces that might, under the right conditions, allow a transition to something else. The strange matter scenario is just one example of this. There might be other cosmic threats we haven't even thought of yet. Other ways that the universe could suddenly reconfigure itself in a way that erases everything we know. The universe is under no obligation to remain stable just because we exist in it. And yet, here we are, against all odds, in a universe that might be fundamentally unstable. We exist, we think, we wonder. We calculate the probabilities of our own demise. And there's something almost beautiful about that. The fact that we're here at all, even temporarily, even precariously, is remarkable. If the universe does convert to strange matter someday, whether tomorrow or in 1,000,000,000,000 years, it won't diminish the fact that we were here, that we experienced consciousness, that we looked at the stars and asked questions about our place in the cosmos, that we loved and learned and built and dreamed, even knowing that it might all be temporary. The possibility of strange matter doesn't make life meaningless. If anything, it makes every moment more precious. Because we don't know how long we have. We don't know if we're living in the last generation before conversion, or if we have billions of years ahead of us. All we can do is make the most of the time we have, in whatever form that takes. Chapter 10. The stability of our universe. We've come a long way in this exploration. We've descended from the familiar world of atoms and molecules down to the quantum realm of quarks. We've traveled to neutron stars, the most extreme objects in the universe. We've contemplated strange-lays, those potentially infectious particles that could rewrite reality itself. And we've imagined the end of Earth, the conversion of our planet to a grey sphere in a matter of hours. Now, as we come to the end, I want to take a step back and think about what all this means. Not just for our physical safety, but for how we understand the universe and our place in it. Let's start with what we know for certain. We know that quarks exist. That's been proven by decades of particle physics experiments. We know that neutron stars exist. We can observe them with telescopes, measure their properties, even detect the gravitational waves they emit when they collide. We know that under extreme pressure, matter behaves in unexpected ways. All of this is solid, established science. But when it comes to strange matter, we move from knowledge to theory. We think strange matter might be possible based on our current understanding of quark physics. We think it might be more stable than normal matter based on certain theoretical calculations. We think it might convert normal matter based on the principles of quantum mechanics and energy minimization. But we don't know. We haven't observed strange matter. We haven't studied it in a lab. We're extrapolating from what we know into conditions we can't directly test. This is important to understand. The nightmare scenario I've been describing is possible according to our current theories, but it's not proven. It might be that our theories are incomplete. It might be that there's some physical mechanism we don't understand that prevents the conversion from happening. It might be that strange matter exists, but isn't actually more stable than normal matter. It might be that strangelets are unstable at all sizes we could encounter. So, what's the scientific consensus? Most physicists believe that the risk of dangerous strangelets is very low. Here's their reasoning. The universe has been running for almost 14 billion years. In that time, countless high-energy events have occurred. Neutron stars have collided. Cosmic rays have bombarded every planet and moon in the galaxy. The early universe itself went through a period where quarks existed freely. If stable, dangerous strangelets were easy to create, we would expect them to be common in the universe. And if they were common, we would expect to see evidence of conversion events. We would expect to see unusual objects in space that could be explained as converted matter. But we don't see that. Everywhere we look in the universe, we see normal matter behaving normally. Stars are burning, planets are orbiting, galaxies are structured the way we expect. The cosmic microwave background, that echo of the Big Bang, shows no signs of large-scale strange matter formation in the early universe. All the evidence suggests that if strange matter exists at all, it's either very rare or confined to the cores of neutron stars where it can't escape. This is reassuring. It suggests that we're probably safe, that the conversion scenario, while theoretically possible, is unlikely enough that we don't need to lose sleep over it. The universe has been testing this possibility for billions of years, and we're still here. That's a pretty good track record. But here's the thing about cosmic risks. Low probability doesn't mean zero probability. Even if the chance of a strangelet hitting Earth is 1 in a trillion per year, given enough time, unlikely things eventually happen. The universe is not obligated to keep us safe forever just because it has kept us safe so far. And that brings us to a fundamental question about how we live with uncertainty. Because uncertainty is built into the fabric of existence. We can never know everything. We can never predict every possible outcome. We can never make ourselves completely safe from every conceivable threat. Think about your daily life. Every time you cross a street, there's a small risk that a car might hit you. Every time you eat food, there's a tiny chance of food poisoning. Every time you breathe, you're inhaling air that might contain harmful particles. But you don't spend your life paralyzed by these possibilities. You take reasonable precautions, and then you live. You accept that perfect safety is impossible, and you move forward anyway. The strange matter scenario is like that, but on a cosmic scale. It's a possibility we need to be aware of. It's something scientists should continue studying and monitoring. But it's not something that should prevent us from living our lives, pursuing knowledge, or finding meaning in existence. In fact, I would argue that the possibility of strange matter makes our existence more remarkable, not less. Think about what it means that we're here. Every atom in your body has been stable for billions of years. The quarks inside those atoms have maintained their current configuration since before Earth existed. The laws of physics have remained consistent enough that complex structures like stars, planets, and life could form and persist. That's incredible when you think about it. The universe could be chaotic. The laws could be changing constantly. Matter could be unstable. But instead, we live in a universe with enough stability and consistency that we can exist, that we can evolve, that we can develop consciousness and ask questions about the nature of reality itself. The fact that this stability might not be absolute, that there might be some rare scenario where it breaks down, doesn't diminish how amazing it is that we're here in the first place. If anything, it should make us appreciate it more. This connects to a broader philosophical idea that I think is worth considering. The universe doesn't exist for us. It wasn't designed with human well-being in mind. It's governed by physical laws that operate regardless of whether we exist or not. And those laws permit things that would be catastrophic for life. black holes that can tear apart anything that gets too close, gamma-ray bursts that can sterilize entire regions of space, asteroids that can impact planets and cause mass extinctions, and yes, potentially, strangelets that can convert matter. But despite all these dangers, despite the universe's fundamental indifference to our existence, we're here. We've survived for hundreds of thousands of years as a species. Life on Earth has persisted for billions of years, and in that time we've done something remarkable. We've looked at the universe that could destroy us, and we've tried to understand it. We've developed mathematics and physics to describe how reality works. We've built instruments to observe distant stars and galaxies. We've created theories to explain everything from the smallest quarks to the largest structures in the cosmos. This is what makes us human, not our physical bodies, which are ultimately just temporary arrangements of atoms, but our minds, our curiosity, our drive to understand, our refusal to accept ignorance when knowledge is possible, even when that knowledge is frightening, even when it reveals that we're more vulnerable than we thought. The strange matter hypothesis is a perfect example of this. We didn't have to think about this possibility. We could have just assumed that normal matter is the only kind of matter and been happy with that assumption. But instead, some physicist looked at the equations describing quark physics and said, wait, what if under extreme pressure strange quarks could form stable matter? And then other physicists took that idea seriously, worked out the implications, and realized it could be terrifying. That's the scientific mindset, following the logic wherever it leads, even to uncomfortable places. And I think that's something to be proud of, even if the conclusion is that we might be living in an unstable universe. Now, let me address the elephant in the room. Some of you watching this might be feeling anxious right now. You might be thinking, should I be worried about this? Is a strangelet going to hit Earth tomorrow? And I want to address that directly. No, you should not be worried in any practical sense. The probability of a strangelet hitting Earth in your lifetime is astronomically low. So low that it's not a rational use of your mental energy to dwell on it. There are countless other risks in life that are far more likely and far more worth preparing for. You're more likely to be struck by lightning a dozen times than to be affected by a strangelet in your lifetime. But should you be aware of this possibility? Should you think about the implications? I think yes. Not because you need to prepare for it or protect yourself from it, but because it teaches us something important about the nature of reality. It reminds us that the universe is stranger and more complex than everyday experience suggests. It shows us that our current stability is a result of specific physical conditions, not an absolute guarantee. And it highlights how much we still don't know about the universe we live in. This kind of thinking, this willingness to confront uncomfortable possibilities, is what drives science forward. Every major advancement in physics has come from someone asking, what if our current understanding is incomplete? What if there's more to reality than we currently see? What if the familiar rules break down under certain conditions? Sometimes those questions lead to beautiful discoveries. The theory of relativity came from asking what happens if you move really fast. Quantum mechanics came from asking what happens at very small scales. But sometimes those questions lead to darker possibilities. Black holes, the eventual heat death of the universe. And yes, strange matter. But even the dark possibilities have value. They expand our understanding. They show us the full range of what physics allows. They remind us to be humble about our knowledge and careful about our assumptions. They teach us that the universe is not obligated to be safe or comfortable or understandable. It just is. And our job as conscious beings is to understand it as best we can, accept what we find, and live meaningful lives within that understanding. So where does that leave us? We've spent 2.5 hours exploring one of the most frightening possibilities in physics. We've imagined the end of our world, not in fire or ice, but in conversion. We've contemplated a universe where all matter might eventually become strange matter. We've asked whether we could accidentally create the very thing that could destroy us. And here's what I want you to take away from all of this. First, the universe is amazing. The fact that we can understand it at all, that we can write equations describing quarks and neutron stars and strange matter, is a testament to human intelligence and persistence. Second, knowledge is valuable even when it's frightening. Especially when it's frightening, because ignorance doesn't protect us. Understanding does. And third, our existence is precious precisely because it's fragile. Every moment you're alive, every breath you take, every thought you think depends on the stability of matter at the quantum level. The atoms in your body have to remain normal atoms. The quarks inside those atoms have to stay bound in their current configurations. The laws of physics have to continue operating the way they have for billions of years. And so far, for your entire life, for all of human history, for the entire history of Earth and the Sun and the galaxy, those conditions have held. That's not nothing. That's a miracle of cosmic proportions. So yes, strange matter might exist. Strangelets might be out there. The universe might not be completely stable. But right now, in this moment, we are here. We exist. We think. We wonder. We learn. We love. We create. And that matters. That has meaning. Regardless of what the future holds, regardless of whether the universe remains normal or converts to strange matter someday, the fact that we're here now, experiencing consciousness and exploring reality, is valuable in itself. Thank you for joining me on this journey into one of physics' darkest possibilities. Keep questioning. Keep learning. Keep appreciating the strange and wonderful universe we find ourselves in. And remember, every day that you wake up made of normal matter is a day to celebrate the remarkable stability that makes life possible. The universe may be uncertain, but our curiosity about it never has to be.